Hi, everybody. After talking in class the other day, I thought it might be helpful to talk a little bit about transesterification reactions here. So just to be clear that we know that we can do them in acidic or basic conditions. So as we have drawn up here, we've got acidic conditions where we're using some type of acid catalyst. Or we can have basic conditions where we're using more like a strong nucleophile type of thing, where it's like an O- that is actually attacking the ester. So these are basic. We got a strong nucleophile. Okay, so we can do both of those options for transesterifications where we're starting with one R group and we want to get to some other R group. So we just want to switch it up to a different type of ester or something. So let's just look at the mechanisms here. So let's look at the acidic one first. So this is very, very similar to the Fischer esterification, right? So it's going to be essentially the exact same thing, except we're going to be using an alcohol instead of a water as our nucleophile. So let's just take an example here. We're just going to do a nice simple one in this. So let's just use methanol. Oops, no, methanol. So we're starting out with that. Let's use ethanol and sulfuric acid. Okay, so that is going to transfer out whatever is on this alcohol to over here. So you're going to end up with an O-ethyl ester instead of a methyl ester. So the mechanism for that, since we're in acid, our first step is going to be to protonate our carbonyl. Okay, now we have a good electrophile that we can have our nucleophile come attack. So our nucleophile is going to be our ethanol here. We can go attack that carbonyl, move the electrons up. We end up with this intermediate. Again, we're going to have to do a little bit of proton shuffling essentially to make sure that that isn't our best leaving group. We want this to be what leaves. So we can have another molecule of our alcohol come in, deprotonate that. And then we can turn around and protonate our methoxy side. Okay, so once we get to here, now we have formed a good leaving group for ourselves. And this is a situation where, because you're already starting off with an ester, you know, obviously you could imagine something like that becoming the leaving group, but just focus on the fact that if you're adding in an alcohol, that's going to be the most likely nucleophile to come in. And keep in mind that we are still trying to end up with a carbonyl. So we're not trying to get to some weird like acetal thing here. We are aiming for a carbonyl. So if this was the thing to leave, that would make it very hard to become a neutral carbonyl. So you're not going to actually end up, you could do that, but it's not going to get you to anything that's a stable product. So we're aiming to get to the stable product. It really helps in these reactions to draw out the product first. And then you can kind of have that mechanism guide yourself there. All right, so now that we have our tetrahedral intermediate and we're ready to kick off our leaving group, we can reform our carbonyl, kick off that alcohol that we just made. Okay, so this has made us methanol, okay, as a byproduct here. And then we can just use that methanol to deprotonate your H. You can also use the ethanol. It doesn't really matter. One of them is going to do it. And then that's going to get us to our final product. Okay, so the key here, just to kind of defeat the equilibrium process, is that we have to have a large excess of our new alcohol to make sure that we replace a sufficient amount of the original ester with our new alcohol. Okay, so we need to have a lot of our alcohol starting material over here so that we can push it to this other alcohol starting material. Okay, so we want to have this to be a very, very small quantity. So this is going to be huge over here with the ethanol, and then it's going to push it to form that product. Alrighty. Okay, so let's look at the basic mechanism. And we'll just put a little note here on them. This is the same as the Fischer esterification. Okay, so the basic mechanism, like we've seen with the other basic mechanisms, it tends to be quite a lot easier because there's less we need to worry about in terms of proton transfers. So if we start off with this ester, and let's just use something like sodium methoxide, you would normally pair this up with the alcohol version of whatever your nucleophile is. So we've got some deprotonated and some protonated. If they react with each other, you're just making more of each of them. So it doesn't really, it's kind of a net zero essentially. And this provides just a good solvent to help us dissolve this in, because that is a solid. And then we have something to run the reaction in, and give us something that can do some proton transfers when we need it. So with this, just like in a normal carbonyl reaction, if we've got the base first, we are going to go straight into the nucleophilic attack. So we can have our OET minus go directly to that carbonyl and push the electrons up onto the oxygen. And then we get to this intermediate. At that point, I don't really need to worry about any kind of protonation to get to my final product. All I need to do is come here, kick off that methoxide. And then I've got my new ester. I've made that. Okay, I could grab an H from the ethanol there, or we can just leave it like this. Doesn't really matter. But you can see how much simpler that is. We just go straight in with that strong nucleophile, reform the carbonyl, kick off the leaving group, and then you've got your new ester. Okay, so the basic one, again, quite a lot easier. It's just all there. Okay, so the other question now is, why can't we do a basic mechanism with the Fischer esterification with a carboxylic acid starting material? So let's look at that real quick. Okay, so why can't we do a base catalyzed esterification of carboxylic acids? So let's look at what happens when we've got a carboxylic acid here and a base. So let's go with sodium methoxide again, why not? So what's going to happen here is if we do our first step, okay, in the ester version, we just went straight and attacked this carbonyl. but there's something that's more reactive than the carbonyl right now, and that's the acidic proton. So this is going to go directly for that proton on our carboxylic acid. Okay, so essentially what we've got going on here is the pK of our carboxylic acid is about 5, and the pK of our alcohol is about 16. So we have essentially just an irreversible step here. So I'm going to change that arrow to single arrow, because this difference between 16 and 5 is so big that we are fully in this scenario here. So that's going to take at least one equivalent, not at least, it's going to take one equivalent of your nucleophile to deprotonate that carboxylic acid. So that's going to happen all first. So even if you had an excess of your sodium methoxide, the problem is it's not a strong enough nucleophile to attack a weaker electrophile. Okay, so remember, this is a pretty bad electrophile. And this is not a strong enough nucleophile. Okay, so this is just going to be no reaction here, and you're going to end up with the carboxylate. Okay, so this is not going to happen. We won't be able to attack that carboxylate anion. So this is just going to be an acid-base reaction and nothing else. So oxygen nucleophiles aren't strong enough to attack carboxylate anions. Oops. Okay, so that's why we can get away with the base catalyzed esterification when we are doing a transesterification, because we don't have any acidic protons here. So we can go ahead and attack that carbonyl because it's neutral, it's still okay. We've got a strong enough nucleophile. But as soon as we end up doing this acid-base reaction first, then we end up forming a pretty weak nucleophile. And even if we have an excess, it's not going to be strong enough to actually attack that carboxylate anion. Okay, so base catalyzed esterification is fine for transesterification, not going to work for esterification of a carboxylic acid. So hopefully this was helpful and clarified a few things about transesterification reactions. And make sure you let me know if you have any questions, and I'll see you all later.